point functions.
Okay, test. Okay, yeah. Thanks, Yvette. Thanks for the organizer for organizing this workshop. So I'm going to talk about multi-party distributed point function. This is a recent work joined with Arushi and Zhihen. So I'm extremely happy to especially give this talk to this audience, where many of the audience have contributed significantly to this line of work. So let's start. The primitive that we are interested in this talk is so-called function secret sharing, introduced by Mingyuan and Yvette. So here we have a trusted dealer who given a function f from some family, and will generate n shares, call them f1, f2 to fn, to n parties. And these parties, taking this local share they got, and the public input x, will do some local evaluation to generate this share y1 to yn. And for the correctness of the function secret sharing, we want that this, the summation of this y1 to yn should equals to the function being shared, f, evaluate at the public input x. And for privacy, we wanted that the subset of parties where you're corrupted, by looking at the shares, you should not be able to know which function is being shared. And for the purpose of this talk, we always assume that it's all but one corrupted parties. And the naive way for doing this is that if you can take just the truth table of this function f and additively share it. So I will use D to denote the size of the domain. So the naive way of sharing this is that every party gets a secret their share that grows with the size of the domain. So for efficiency requirement, we want the shares to be sublinear in the domain size. Okay. So to know what the distributed point function is, we first need to look at what the point function is. And this is basically a very simple function where it's almost zero everywhere, except for at one point, which I denote by alpha, and it should be equals to some arbitrary beta defined by the function. So this is a point function. And the distributed point function is basically function secret sharing for the family of point functions. Okay, so this point function seems like a very small family of functions. Why do we care about function secret sharing for such a family? And it turns out that this distributed point function is actually a very, very useful primitive that is being used in numerous many applications. So for example, in Peter's talk yesterday, you have already, I don't think Peter mentioned the word distributed point function, but for all those computationally pure private information retrieval, for one function, basically the distributed point function is underpinning primitive. And you have seen from Peter's talk just now that we also have this fascinating primitive called pseudo-correlation generator, where the distributed point function is really the core primitive that enables this. And from yesterday, we have the talks about structure aware PSI, or fuzzy PSI, where I think Jasper mentioned that one of the ways to get this fuzzy PSI is through the distributed point function. And there are other primitive, many applications in MPC that uses DPF extensively. So, okay, so hopefully convinced that DPF is an amazing primitive. So what do we know about how to construct these distributed point functions? So if you limit it to the two-party case, things actually are very, very good. So even in the very first paper where distributed point function is introduced, Gilboa and Nishai already proved that one function is sufficient. So this is a symmetric key primitive. And thanks to the follow-up work by Yvette et al., now the share size of this DPF is also very, very short. It's just the lambda times log D. I don't think there's even constant to that, it's just lambda times log D. And there are also works that's not just limited to point function family, but for the families that are related to the point function, like multi-point function and comparator function, and so on and so forth, where we also have a lot of works that optimize the efficiency of these function secret sharings for these larger families. And in the DPF vanilla setting, we have a trusted dealer sending out these shares. There are also works trying to optimize the distributed setup for setting up these DPF shares. So my point here is that in the two-party case, things will have received a lot of attention, and many works have been trying to optimize efficiency. So what about the multi-party case? If you look at a multi-party DPF in the minicrypt setting, essentially the only known construction we have is from this paper from 10 years ago by Boyle et al., which achieves this efficiency 2 to the n times root d, where n is the number of parties. So this is much, much worse compared to the two-party case. And basically, there has no progress on this in the minicrypt setting since the last time we have the program at Simus. And to be thorough, if you want to go beyond minicrypt, there are some constructions that construct DPF. In particular, if you are willing to assume learning with error assumptions, then we have this beautiful work by Dodis et al., where you can get basically polylog key size. But interestingly, besides LWE, I don't think there's any work that can get beyond square root of d. There are some recent works in the context of getting sublinear MPC, where you get different levels of sublinearity. Some might not be as good as root d, and some maybe work even with a fixed number of parties. But yeah, that's basically how things are right now. Okay.
Can I ask, are you assuming all but one corruption here?
All but one corruption. Yeah. Any more questions? Yes.
What about the 2 to the n, like the,
No, that's what we do, the 2 to the n. Yeah. Okay, so the next thing I want to tell you that is the sort of the multi-party DPF. Is it the lack of progress? Is it because we don't care about it, or maybe the two-party cases suffices? Actually, this limitation in the DPF construction where we can only do two-party efficiently but not multi-party also poses a limitation on all these applications, fascinating applications enabled by DPF. For example, I think Henry in yesterday's talks mentioned that we don't have a three-party peer scheme where from one function where the communication is polylog. If you have a three-party DPF that has polylog key size, then you would solve Henry's problem. To solve Henry's problem, you don't necessarily need to go to DPF, but it's sufficient to solve his problem. And in the application of pseudo-correlation generator, right now we can generate multi-party correlations, but because of the DPF limitation, if you want to do it, you have to generate pairwise correlations first to get a multi-party correlation. That incurs an overhead in the quadratic in the number of parties. And ideally, we would like remove that. So if we have a multi-party DPF that matches the efficiency of two-party cases, we can achieve that. And in other applications of MPC, if you want to go through the DPF-based constructions, then this two-party limitation is again will manifest. Okay. All right. So this is the problem we want to look at in this work. And in particular, the question we wanted to answer here is that, can we at least improve the dependence on the number of parties in this construction? So maybe here we are exponential in the number of parties. Can we make it polynomial in the number of parties? So we can have efficient multi-party DPF for any number of parties inside minicrypt. And as always, if we pose a question, the answer is yes. And in this case, we construct such a multi-party DPF with the share size being n cubed times square root of the domain size. Where throughout this talk, whenever I have the asymptotic notations, hides the polylambda factors. Okay, and just to disclaimer that this is by no way efficient, and even compared to the two-party case, there's still square root in the domain size, so it's the only theoretical interest. Yes?
What's the degree of lambda?
This dependence should be something like lambda to 3, lambda to 4. We haven't been keeping careful track of it, but yeah.
Is it by to compute the concrete break-even point, or will it become better than the existing construction?
Yes, we haven't done the calculation yet. Okay, any question at this point?
would you minicrypt to mean just one-way functions?
Just one-way function, black box use of one-way function. Okay, great. So now let me just jump to the technical part of give you a high-level idea of how we construct this multi-party DPF. So to do that, let's first recall how BGI-15 constructed their multi-party DPF. And in particular, we even started with the two-party case because it's instructive to start with the two-party case. And remember that in DPF, basically the truth table of the DPF is 0 almost everywhere except at one special point where it's non-zero. And the way they constructed this multi-party DPF is you first divide this length d vector into square root d many chunks. Each chunk has length root d. And to share this among two parties, what you do is very simple. For each chunk, let's say you're giving the shares to party P1, for each chunk you give it a PRG seed. And for the second party, you give them almost exactly the same thing, that for all these non-special chunks where everything's 0, you give the same seed, and here too. For the special chunk where you need to have this non-zero values, you sample a different seed and give it to the second party. And in order to expand this seed into the additive sharing of the truth table, what each party does is just to apply the PRG on top of the seed they get, right? And you can see that if we are in this non-special chunk, because they get the same seed, when they apply the PRG and XOR them, you will get a sharing of 0. The problem is that for the special chunk here, that when they get different seed, they will sum up to something that is not what we want. Right? And to fix this, there's a standard trick, which is to use something called correction string. Here, this correction string is basically the offset you need to make this agree with the indicator vector that you're trying to make it goes to. But remember that we cannot tell the evaluator, the P1, P2, which chunk to apply this correction string. So the way to do that is that you give each party additionally some control bit, which is an additive secret sharing of either 0 and 1, basically indicating which chunk is the special chunk. And now your local evaluation is to expand the CRG, expand the PRG, and then apply this correction string conditionally based on the conditional bit you got. Right? So in this way, if it's a non-special chunk because it's additive secret sharing of 0, it doesn't affect the final evaluation. If it is the special chunk, then you basically offset this by this, which you will get the correctness. Okay. Makes sense? So now for the privacy part, the important part here is that why does this correction string doesn't leak anything about which chunk is the special chunk? And the reason here is that this pseudo-random string is basically a one-time pad that masks this information related to the function. And the reason is that no matter which party you corrupt, there exists the other seed which you never see. So the contribution, for example, if you corrupt party P1, the contribution of this blue seed will still be pseudo-random. That's why it hides which this indicator vector here. Okay. And finally, observe that the efficiency of this construction is root d because you are sending root d many seeds. If you're wondering why can't I send smaller seeds, it's because you also need to send the correction string, which grows with the stretch of the PRG. So the sweet spot is where you get square root of d. Okay. Make sense? Questions?
Here, is it okay if I interpret the output of the PRG as a characteristic to field element?
Good. So I think, so first of all, like when you give us, if you are treating this PRG output, you can regroup them as field elements. But if you want them to cancel, you have to give them a sign. Like if you give one party the positive sign, the other party negative sign, then you will cancel. I think for our scheme in a this is a two-party case. In our scheme in a multi-party case, you can get it. I think there is some issue with BGI-15, so I will maybe mention that when I get to it. But yeah, to our scheme, it's not important. It's a characteristic too. Okay, so now for two-party DPF, we have very efficient construction. Why am I telling you this? So the very clever thing that BGI-15 observe is that you can actually extend this to the three-party case. And to do so, instead of giving each party one seed per chunk, you give them a bunch of seeds. So what you do is that, for example, for this chunk, for every chunk here, for the non-special chunk, you sample 3 seeds, 0, S0, S1, and S2. So for example, you give S0 twice to P1 and P3. You give S1 twice to P1 and P2. And you give S2 twice to P2 and P3. So the way you are going to expand these seeds is that you expand the seeds individually and then add them up together. And if you do that for these non-special chunks, what do you get? You will get 0 because every seed is shared twice, right? So they will cancel each other, and you will get 0 here. Now the question is that what do you do for the special chunk here? And the way they do it is that instead of using this S0, S1, S2, they use one additional PRG seed, let's call it S3. And you only give 0, 1, and 3 once, and you give S3 to all the parties here. Okay? Now if you add them up, again, expand each seed and add them up, you will see something like the following. The one important thing we'll observe, just like the two-party case, is that this is sum is pseudo-random, no matter which two parties you corrupt. For example, if you corrupt P1 and P2, because S2 is a seed that only sent to party P3, this is a dedicated seed to P3, this string is pseudo-random because there's a contribution from S2. Right? So, of course, I didn't put the correction string on the slide, but you also need to apply the correction string to get the this evaluation of the special chunk to be the indicator vector. But the pseudo-random guarantees that the correction string will be not leak any information. Now, there's one thing that I haven't talked about is that why is it okay to use two different ways to share this seed? One way using for the non-special chunk, the other way for the special chunk. The reason is that if let's say you corrupt party P1 and P2, you look at the seed that you get, it's actually the same distribution. Basically, you get one seed twice. For example, in the special chunk, you get S3 twice, and then you get 2 other seeds. And this is the same case for the non-special chunk, where you get one seed twice and 2 different seeds. Okay, makes sense? So this is why this seed distribution process is indistinguishable from the for the special chunk and the non-special chunks. Okay. And the first thing, the BGI 15, this is a 3-party case. They can also extend it to more than 3 parties for any number of parties. But the first thing we do when we take their construction is that we abstract out this what we call a special combinatorial design. Essentially, what we do is that we will this seed distribution process as 2 bipartite graphs. So G0 is the way you distributed this seed for non-special chunks. G1 is the way you distributed this seed for the special chunks. So for example, recall that in the non-special chunk, there are 3 seeds, each given to 2 of the parties. This is exactly what G0 is looking like. There are these 3 seeds, which is given to every 2 parties. And for the special chunk, we are giving this 3-party S0, S1, S2 each once, and then 1 seed to all the 3 parties. This is exactly what G1 looks like. Okay? To use this 2 bipartite graph to distribute the seed and get a multi-party DPF, you need the following 3 properties. The first property that you want G0, which is the way you distributed the seed for the non-special chunk, to have even degrees. This is ensure that they will cancel each other when they expand the seed and add them up. So if every seed contributed even number of times, they will cancel each other. And the second property that we want is called pseudo-randomness property. And this is essential to say that for the G1, for the special way of distributing the seed, we want per party, there is a dedicated seed which only goes to that party. And it doesn't go to any other parties. And by distributing the seed using G1, you can ensure that this correction string that we will get is going to be pseudo-random, no matter which n-1 party you corrupt. And finally, we want the privacy guarantee, which is to say that this two-way of distributing the seed is indistinguishable to each other. This means that whatever two party that I corrupt, for example, if I corrupt P1 and P2, the subgraph induced by G0 and G1 looks indistinguishable. So I have highlighted this for you that these thick red lines basically the subgraph you get when you corrupt P1 and P2. And they look exactly isomorphic. Okay. So given this way of distributing this special combinatorial design, if you have all these three properties, they basically, and you can plug it into the BGI-15 template to get a multi-party distributed point function, where you again divided the vector into root d many chunks. Each chunk has length root d, and you distributed the seed exactly according to G0 or G1 based on if it's a special chunk or non-special chunk. And these three properties, the one that guarantees that you will have correctness and privacy for your DPF construction. Any question at this one?
You don't need the right vertices have even degree, right? You could say they all have the same degree, and you use like characteristic D instead of characteristic.
This is the minimum thing we require. So yeah, you can, if they all have the same degree, that also works, but it's stronger
If they all
requirement.
have degree 3, then you could sum things in characteristic 3 probably.
Sure, but
Then you need n-2, I think.
yeah, maybe, yeah, we haven't thought about it. Yeah, that's also a cool idea.
Related to the question of general characteristic, this instruction is specific for characteristic 2.
Yeah, this abstraction is specific.
No, you can interpret this modulo plus minus 1. And then the it extends. Subgroup plus minus 1.
The basic construction of BGI-15 does not work
Yes.
over general
Yes.
characteristic.
So if your graph only have degree 2, then this abstraction can work for any field by giving us flip sign. But BGI-15 has more than degree 2. Yeah.
What about the pseudo-randomness? Like, when you relax this property?
The pseudo-randomness is because when you
I see why this suffices. I'm just asking, couldn't you use something weaker than this?
you're saying that this is a distinguished advantage is bounded by something. Is that the weakening you are thinking of, or?
I'm just thinking of some of the things don't cancel out. At least let's think about it. I mean, I'm not sure whether it's good for PLC, but say for random walking.
Right.
Unless things start completely, you have pseudo-randomness strings, right?
But the thing is that if I
Fine.
if I corrupted any subset of parties and see every possible seed, so I can see every possible pseudorandom and do linear combination. Yeah. Right. Any more questions? Okay. So the thing I want to notice that is that this template for constructing multi-party DPF, your efficiency will grow exactly with the size of these graphs. And in particular, the number of edges in this graph. Okay. Now, I promise you that BGI-15 can do any number of parties. Let me quickly tell you how to do it, because the construction is so nice, I have to tell you. So this is the construction. I drew it explicitly for 3 parties. And if you notice that basically what G0 and G1 has is that for G0, you have every possible node with even number of neighbors. For example, if there are 3 vertices on the left, it can have degree 0, degree 2. All possible degree 0 and degree 2 nodes are in G0. And for G1, you basically have degree either 1 or 3, all the even, all the degree vertices, and they are all here. And the reason why this works is that first for correctness, we want G0 to have only even degrees, which by design it is true. And we also want that G1 has a dedicated seed per party. And this is, again, true by design. And then the final tricky thing to see that why is any induced subgraph is the isomorphic. This is because the parity will be gone, will no longer matter if we remove one party from this graph. Okay, but notice that the size of their combinatorial design grows exponentially in the number of parties. To support n vertices on the left, you need 2 to the n vertices on the right. And in our paper, we proved that this, if you want to have a deterministic way of constructing this special combinatorial design, you have to use 2 to the n right vertices. So in that sense, BGI 15 is optimal. I won't tell you how the lower bound works, except I'll just say that this is heavily inspired by the positive construction. You sort of reverse engineer and see that everything is needed there. Okay. How many time I have left? 5 minutes. Okay. Okay. So now that we seem that we hit a barrier and we can't do anything deterministically, so what do we do next? We go to randomized constructions, and this is exactly what we do. So for us, the way of we're sampling G0 is probably the first idea you can think of. We basically sample a random graph, and every vertex here has 2 random neighbors. The important thing is that we sample these neighbors with replacement, so they could go to the same party. So that I would denote by the blue, by blue. And for G1, we additionally sample some degree 1 seed with degree 1. And I will sample T Manning for these degree 1 vertices and L Manning for the degree 2 vertices. So G0 is only the blue part, but G1 is actually the entire thing, blue part plus the green part. So let's check the property that we need. We need G0 to have correctness, which means every node should have even degree, which by design holds. For pseudo-randomness, we need G1, which is the complete thing, to have a dedicated seed per party. This will hold if you throw enough number of seeds here, which will make, means that the number of seeds in the blue part has to be grow linearly in n. Now the tricky part to see is that why this privacy hold. And let me quickly tell you why this hold. But by first glance, it might look like they should not hold because these 2 graphs looks completely different. One is the subgraph of the other thing, so it looks like they should be distinguishable. The thing to notice that is here, if you corrupt a subset of parties, what do you see? You basically see a bunch of seeds, some shared twice, some shared once among, in your share. So the first thing to notice is that you only need to care about how many seed you see once and how many seed you see twice. Condition on those counting, the actual configuration of the distribution is basically random for both G0 and G1. So we only care about how many seeds for each single times and twice you see. So I denote them by S for the single times and T for the you see twice. So then we only need to care about the distribution of S and T for G0 and G1. The next thing to notice is that T is actually identically distributed for both G0 and G1 because what seed can you see twice? Only come from the blue part. And the blue part is the same for G0 and G1. So T is identically distributed. So now condition on T, what is the distribution of S? The distribution of S is basically some Bernoulli samples each with some bias. This is because for G0, the seed you see single times is basically whatever left. Out of these L Manning seeds, you already know that T of them you see twice. So the rest L minus T things, you might see them once, you might see them 0 times. This is a Bernoulli distribution with bias roughly 1 over n. For G1, this is basically whatever G0 have, additionally shifted by this blue additional part, which you sample the seed once. And I will just use one picture to show you why this should be could potentially be indistinguishable. This is basically because G0 is some random sum of Bernoulli distributions, which is distributed something maybe looks like a Gaussian, and if we shift it by some amount n, as long as the standard deviation of this blue distribution is large enough, then this shifting will be smudged, noise smudged by the blue distribution. Okay, so I was also planning on giving you an informal discussion of why the L needs to be n to the fourth power, but in the interest of time, I'll skip that. So basically, to sum up, we have in this work, we abstract this special combinatorial design and use the BGI template and construct a randomized special combinatorial design with size n to the fourth power. And notice that this is the total number of seeds. So per party, the share size is n cubed times root d. And one thing I have not mentioned is that this is only weakly secure because the distribution, you can only get it inverse polynomial apart. And we need, thanks to this work by Boyle et al., there's a generic way of amplifying weak DPF to strong DPF. So that takes care of that issue. So okay, let me just end the talk with some open problems. First is the concrete efficiency of the construction. This you can, for example, one thing we didn't do a very good job is the dependence on the security parameter. That's one avenue for improvement. And also, what can you do for other functions beyond point function, their optimization, and also DKG for generating these shares. And then the final thing, which bothers me a lot, is this square root of d. Can we go beyond that? You can first ask this question in Minicrypt. And I guess a lot of people have also tried this. If we cannot prove it, maybe you can prove a lower bound for it. And you can also ask this outside Minicrypt, and basically anything beyond LW is open. And finally, I have been only talking about a full threshold case. We also would like to a threshold version of DPF that in particular would imply a threshold pseudo-correlation generator. So that's also a very fascinating but maybe challenging questions. And with that, I will end my talk here.
Any questions?
Yes.
So say that you relax this
Yeah.
You can relax it significantly. It doesn't give you something.
Oh no, it has to be grow with lambda. It has to grow with the security parameter.
So can't you hope? I'm not sure. Can you hope to go below like n cubed in this case?
Yeah, we don't know, but at least if you don't allow, if you are not in the all but one corruption, I can see some improvement. Or all but one, I'm not sure if n cube is optimal or not.
Okay. So again, the question is about 0.9.
Oh, 0.9n. Yeah. Then even for the combinatorial design, you don't need per party dedicated seed. You can have just every.
What would be the number? So what would be the overhead in terms of as a function of n?
I think the dependence on n can be completely removed if you have a fraction of corruptions. Yeah. Yes.
You mentioned there's this privacy amplification step. Like, what is the overhead that it adds to the construction?
Good. So basically, what they do is that you encode. You need to do any locally decodable code to encode the database into a longer database. It can be near linear. Every one query to the original code is now become multiple queries to the locally decodable code. And I think it will grow inversely in this epsilon here. Yeah. But one point is that now you don't have to evaluate at any point. You really need to evaluate the entire domain because of you have to do the encoding. Yeah.
All right. In that case, let's thank the speakers today. You're now free for lunch. A reminder for those who signed up and for the junior senior lunches for today, including myself.